from the assignment? Anything that you want to go over? Questions? Yes? No?
Can you do number 23?
Yeah, we can take a look at 23. Okay, so directions in this section of problems tell you to evaluate the infinite geometric series. When they say evaluate a series, what are they always talking about, regardless of whether it's arithmetic or geometric? Find the sum. Okay. Now, this one is an infinite geometric series, which we talked about. There's a specific formula for that, okay, on your sheet that was in your notes that we talked about. And so that formula that we're looking at is first term over 1 minus the ratio, okay, in order to find the sum. And yesterday we talked about why, even though it's infinite, why you can actually find the sum. Oh, yesterday's? No? Oh, gotcha. I'll tell you which ones to do too. So as you take a look at this, the reason why you can find the sum in a series that keeps going forever is very simple, because if you notice, we're adding less and less and less every time. So if we kept going, we're only 4 terms in. If we kept going at like 100 terms, 1,000 terms in, eventually you're basically adding nothing. So even though this does keep going, it gets so small, the number that you're adding, that it kind of ends, is the idea. If you can think of it as basically ending, that eventually you're not adding anything. So we have the first term. That's pretty straightforward. Okay, so for the sum, we've got 5.4 over 1 minus. How do I find the common ratio? Yeah. It's called a ratio for a reason, okay? Because you take the ratio, how do you get to the second term from the first term? So to find r, we just take any 2 consecutive terms, doesn't matter which 2 they are, and take the second one divided by the first one. So in this case, I'm going to take negative 3.24 divided by 5.4 and get an answer. Even if I took the third and the second one, if I took 1.944 and divided it by negative 3.24, you should get the same ratio. If it's geometric, that ratio should be the same every time. What do you get? What is the answer for that? Negative 0.6. So we've got a negative 0.6. You can leave that as a decimal, or that's negative 3/5 if you wrote it as a fraction. So that means this negative 3.24 is negative 3/5 of 5.4. 1.944 is negative 3/5 of negative 3.24. Okay, so there's your common ratio, which we can now plug in. In this case, because I'm subtracting a negative, I'm actually adding. So we end up with 1.6 in the denominator. And what is 5.4 divided by 1.6 should get you to the answer, which is what? 3.375? There's the sum. If this kept going, that sum would approach 3.375, which 0.375 is 3/8, so 3 3/8. So biggest part on this one, you had to find the common ratio. Okay. Any other questions? Anything else you want to go over from the worksheet? Anything at all? Last chance. Any questions? Okay. Either that means you know what's going on, or you don't have any questions because you didn't do the work. One of the two. Okay. So, fair enough. Either way, we're moving on. Okay? So, let me go into the actual lesson for today then. And it's like I said, it's not really much of a lesson. It's just a couple of application problems. And I have it copied off for you, so let me give you that. So you don't have to write the whole problems out. All right, so if you take a look at the lesson, I'm going to modify it even from when I made copies of it. We're going to get rid of a few things. I'm going to modify the actual assignment as well, like I said. But all we're really adding in is a couple of different applications today. So if you take a look, just a quick reminder from back, we said that a geometric sequence is really just an exponential function. Okay, that's all. So we're going to go back and revisit applications of exponential functions here a little bit. So remember the compound interest formula that we talked about, where P is the principal, the starting amount, okay? Kind of like your first term in a geometric sequence, that's your starting amount, okay? R is your interest rate. Remember, you're going to take the interest rate, normally it's given to you as a percentage, you need to rewrite it as a decimal when you plug it into that formula. N is the number of times per year that you're compounding. So it could be once a year, could be twice a year, could be every week, could be 52, could be whatever. But N is the number of times that you're compounding. T is the total amount of time. Okay, so if you're going to look at 5 years from now, 10 years from now, 100 years from now, how much money would you have? Okay, that's what T is. And A is your ending amount after that amount of time. Okay, so after 5 years, how much is sitting in the account? After 10 years, how much is sitting there? So just a reminder of this again. Okay, that's if things are compounded more than once a year, or even if it is once a year. The other portion was if you remember, if it was continuously compounded, basically if the clock is always running. Okay, this would really give you like the maximum amount of money you could have. That's really what this is. It gives you the maximum amount that could be there after 10 years, after 5 years, whatever it is. And basically the same stuff applies. Interest rate is a decimal, T is time in years, P is your principal. Remember, E is the actual number E on the calculator, that 2.718, that's what that E is. All right, so if I give you, let's go to the first example here. And we'll do it the way we did back with exponential functions. But then I'm going to very quickly relate it to what we're doing now, okay, and how you can look at it in a different format. So first off, given that information, the fact that we're starting with $2,000, you're going to put it into an account that's going to earn 9% interest compounded monthly. How much would we have 10 years later? First question, which one of those formulas would I use? Okay, yeah, the first one. Not the PERT formula. This is not compounded continuously, so it's not PERT. So first thing, we're using that formula. Okay, there's your formula that we're going to use. And like I said, for this example, we're going to kind of do it just using the formula for now, and then we'll relate it to the geometric sequences that we were working on. All right, where does the 2,000 go? P, that's your starting amount. That's the principal. Okay, so P is 2,000. What about the 9%? What are we going to do with that? 0.09 goes in for R. That's your interest rate. What about, what is N in this problem? 12, because we're compounding monthly. So that's what N is representing, is that you're compounding it 12 times a year. So just a quick reminder as well, as you're hopefully as you're understanding this, when you take the interest rate, the reason why you divide it by the number of times you're compounding is because that 9% is over the course of a year. So at the end of the first month, you only get 1/12 of that 9%. End of the second month, you get another 1/12 and another 1/12. That's why you're dividing it by 12, okay, just as a heads up. And then T in this case is 10 years. So ultimately this exponent When we plug all that in, it should look like that. Okay, there's what we have. With just taking the numbers from the problem and plugging them into the right spots. So ultimately then, if we start to simplify this a little bit, if I actually divide 0.09 by 12, if I multiply 12 by 10, you end up with, oops. Let's try that again. You end up with this. And so once again, what that 120 is actually representing, that's the total number. The exponent turns out to be the total number of times you're compounding over the course, in this case, of 10 years. You're doing it 12 times a year for 10 years. That's what the 120 is representing. Okay? Total number of times that you're gonna multiply. And then at that point, if you type that into the calculator, then you get the answer that 12 years later, or 10 years later, excuse me, you end up with that $2,000 has turned into $4,902.71. So you have about 2.5 times what you started with. So that's what we used to do. If we then relate it, if we take this last step right here, and you look at the next slide on in your sheet here, that last slide is that last step is really just that. That's what I want you to recognize. Notice this 2,000, that's really a sub 1. It's your starting amount. It's your first term. If I were going to write out this dollar amount in terms of a sequence, the 2,000 is your first term. Okay? It's the first amount of money you started with. Once we simplified everything down, what is the 1.0075? That's your rate. That's your multiplier. Every month, you are multiplying by 1.0075 to get how much you would have at the end of the month. And then you do it again at the end of the next month. And again at the end of the next month. And again and again. And that's like I said, all this was, once we simplify, is just a geometric sequence. 120 times, because you're doing it over the course, you're compounding 120 times over the 10 years. Okay? So that's what I wanted you to be able to see, even though we're still using a formula, is really just a geometric sequence is all we're doing. Okay? Making sense, hopefully? So you might have, today you're not going to have to worry about this, but tomorrow as we get into a few different things, I'll start giving you a couple of different types of problems to work on. Okay? All right, so here's the other one. I'm going to actually, in your packet, ignore example 2 in your packet and go to example 3. I got rid of it after the fact because I decided not to do that one. So go to example 3, the ball drop problem. So if you notice in this problem, you take a ball and you drop it from 50 feet, it rebounds to 30 feet, and we're going to try to find the total distance that the ball travels up to the 6th time it hits the pavement, assuming that the rebound height is a constant ratio. Okay? We have to kind of assume it in order to fit with what we're doing. Okay? So first thing I'm going to do, I'm going to start with just kind of a picture of what's happening, just so you can see that and we can refer back to that picture. Then we'll go to the geometric sequence side of things. So if the ball starts, let's say right here, and that is 50 feet off the ground. You drop the ball, comes down, hits the ground. And then it bounces back up, but not the full way. And then it goes back down and hits the ground again. But then it bounces back up, but not the entire way. And then it comes back down and hits the ground again. And so on, and so on, and so on. Okay, just like a ball does anytime you actually would do this in real life. So if you take a look at this one, ignoring the numbers and stuff for a second, where does the actual pattern begin? If we're looking for patterns, that's what this chapter is about. Where does the pattern begin? Once it hits the ground. From here on, if you notice, it's that same, they almost look like parabolas. Okay, parabola, smaller parabola, smaller parabola. There's the pattern right here. That's what we're going to take a look at. And we'll bring the 50 back in a second. Okay? So first question, if we go through and we start off with this. If the pattern is starting once it hits the ground, and then it rebounds, it comes back up to, we said this height is 30 feet. And notice the question. You got to be a little bit careful on this. The question says find the total distance that the ball travels. So it is going up, it's going up 30 feet and then also back down. So on that bounce, it actually traveled a total of 60 feet. 30 up and then 30 back down. Does that make sense? Okay, as you go up and down, it's got that total, that first bounce is a total of 60. Now, here's the question. And then I'm going to add here for a second. We'll go plus. Now I have to do the next bounce. And then the next one, and then we'll go from there. That's where the sequence is coming from. How do I figure out the height of the next one? What is it? It's what? It's not 10.
18.
Where's 18 coming from? You're right. How'd you get 18? If you take a look, when we say in parentheses, assuming a constant rebound ratio, R in this case, if it started at 50 and then went, the next height was 30, assuming that ratio keeps going, just like we did in that homework question, take the second term, divide it by the first. If it's coming back up 30 out of the 50, 30 out of 50 is 3/5. So that is your rebound ratio. It's going to always come back up 3/5 of the way. And then bounce 3/5 of the way, 3/5 of the way. So what would the next amount be that I would add? 36. Why 36 and not 18? Because it's got to go up to a height of 18 and then back down as well to get the total. So we would add 36 to the next one. How would I find the next term? What would I do? Multiply by 3/5. Yep. We can take that total distance now and start. Now we can start the pattern. We had to kind of get there, but now we can go with it. What's 3/5 of 36? What do you get? I think it's a decimal if I remember right. What is it? 10.8 would be the half, right? So 21.6. Okay, so next one is 21.6 for the total distance. How many more terms do I have to go?
6.
I have to go till it hits the ground the 6th time. So how many times is it actually going to bounce? 5. So I need a total of 5 terms here. So we can go, we'll do this one by hand and then I'll show you the formula part of it as well, just so that you understand. What would the next one be? What would the next thing I add? 12.96, that's the total. Yeah, that seems right. So total distance traveled on the next bounce, up and down, would be 12.96. And finally, how about the last one? Okay, yep, that sounds right. Plus 7.776. So there's the 5 bounces, if you will, okay? From here, first one, second one, third one, all the way up until it hits the ground the 6th time. What's the one last thing that I have to keep in mind? And actually, we'll talk about that in a second. Never mind. I'll do it a different way. What is it? Not half the 50, but the actual 50. Normally, this would have been like 100 if we put this whole thing in, but we have to add that 50 back in at the very end as well, okay? Because it did drop from a height of 50, and then the pattern began, okay? So I'll add the 50 at the end. Add those numbers up. What do we get? Add those numbers up. What do we end up with if we put all of this stuff together? Ooh, that was not very good. Should be in the hundreds. 100 what? What is it? What was it? Point what? Okay. So this, correct me if I'm wrong, this is 138, right? This is 138.336. There's the different actual bounces. And then, like I said, I told you we were going to come back. Don't forget the 50 feet that you dropped it from. You got to add that back in at the end. Okay? The pattern is here, but then if we add the 50 back in, you get a total distance traveled of 188.336 feet. Okay? There is the total distance that the ball traveled. Okay? This is the actual starting from here. That's all of the bounces. But you got to add the 50 feet that it was dropped from as well. Okay? Now, quick part of this as well. Because I don't necessarily, because if I asked you on the 6th bounce, so this wasn't too bad, I could find those pretty quickly. But what if I had asked you on the 15th bounce? Okay? Then you'd have to keep going and say, all right, now let's find the next one, and the next one, and the next one. So instead, here's the other part that I want you to see. We could have done this part of it from the 60 to the 7.76. I'm hoping you're seeing that. That's just a geometric series, is all that is. Once it hits the ground, it's the ball, the height of the ball, or what it's traveling, is just a geometric series of numbers. So if we go back to our series formula for a second, just to kind of confirm, I'm going to show you the other option. Sum of what? How many terms? 5. Thanks, Brian. There's 5 terms, because again, the pattern starts once it hits the ground. Okay? So we actually are only adding up those 5 terms, and then again, we'll add the 50 back on. So it's going to be the sum of 5 terms. If we use our geometric sequence formula, okay, the one that's on your formula sheet, it says a sub 1, which in this case, there's the first term we're going to take the sum of. It's the 60. Okay, that's the first bounce. The total distance traveled on the first bounce. So that's 60. 1 minus. What do we say R was? 3/5. Okay, ball height is always coming up 3/5 of the way. So we've got 3/5. We already said n is 5. Oops. Get that out of there. And then we would have 1 minus, in this case, 3/5. N is 5. We're taking the sum of those 5 bounces, if you will. Type that into the calculator and tell me what you get. And again, part of the reason I'm having you type it into the calculator is that's a skill in itself. It's one thing if you can write it, it's another thing if then you can actually type it in correctly with the right parentheses and actually get the answer correct. What does that equal if you type it in? What do you get? Should be a number that's up on the board already.
He said no.
This is why I'm having you type it in. Like I said, it's a skill. Remember, type in the numerator first. Make sure you put the parentheses and stuff in. Okay? And then remember when you type in the denominator, if you're going to type it in directly, don't forget to put parentheses around the whole thing so you're telling the calculator, divide by that whole quantity, not just the 1. What number on the board should that equal?
138.
You should get the 138.336. That's what we took the sum of. It was all of the bounces. Okay? Which means once you get that, then the only thing left to do, just add that first 50, the height that you dropped the ball from. And then you've got the same answer. Okay? But you should get that 138.336 is what you should get when you type that in. Okay? Okay? And if you're struggling with typing that in, I'll come around once I turn you loose here and let you work a little bit. I'll come around and we'll make sure you can get it. Okay? Because like I said, setting it up is one thing, but then I want to make sure you can actually get to the answer and finish things off. All right, so here's what I'm going to have you do. So your assignment for today, I modified it immensely. Originally, you can see it was problems 1 through 24 and 27. I have now changed it to 1 to 23 odd.
What a guy.
Okay? And I'll give you the assignment here in a second. Mainly because you've now had multiple worksheets that have had 20 plus problems on them. And it's still mostly the same type of idea, so that's why I'm kind of cutting this one in half. So that hopefully at this point you're starting to get the idea, or you're mostly getting the idea. So we'll kind of finish this off. Let me give you the assignment, and you've got the rest of the time. If you're still working on old assignments, if you have questions, you can be doing that. Otherwise, if you're all caught up, then you can start working on this. Like I said, I think there was a couple of people in my first hour class that actually finished this assignment before they left, and didn't have anything for homework. Okay? So, let's go to work.